Welcome back, Eigen people. Make sure you guys like, share, comment, subscribe. As we've said for the billionth time, I'm sure you're sick of hearing it.
Yes.
And guys, check out Eigenbros.com, Twitter, Eigenbros, Instagram, Eigenbros, TikTok, Eigenbros 2, and then patrons, guys. We love you. We appreciate you. You're smart. You're loyal.
Yes. And at this time, this is the time we need you the most. Support an Eigenbro.
Support one.
Feed an Eigenbro. Please help me pay.
The boy needs more than rice and beans, you know?
Yeah. I quit my job to do this full time.
Well, don't lie. You just quit your job.
I just quit my job. It was too much.
Yeah.
But anyway.
Yeah. Eigenbros. Patreon.com/Eigenbros. If you guys want an extra 30-minute podcast, me and Juan riff and talk about BS, if you just want some extra content, and then you got access to the Discord, and that's pretty much it.
Yeah.
Anything else?
I think that's it.
Yeah.
Let's get to it. I've been reading, this topic was brought to me from a article that showed up on Big Think.
I was wondering where you got this.
Yeah, the CCC, or Roger Penrose, as some of you might see in the thumbnail. CCC. Yes. Yeah, that's good. What we're talking about is essentially a theory of the universe, answering the question of the Big Bang.
Before the universe.
Yeah, really, before it's asking us. It's trying to answer the question of the Big Bang.
Right. It's one of these theories that kind of boldly goes where no other theory dares to venture.
Exactly.
Which is kind of cool.
Yeah,
you don't really hear about that often.
No, you don't, because I think it's hard for people to tackle the logical inconsistencies, right? Yeah.
Well, it's just kind of like, it's like what could have existed before anything that we could possibly measure. It's almost like, why even ask that question?
Right.
But of course, who the only gangster out there who would even attempt such a thing, Roger Penrose. So
my name is Roger Penrose. I am an emeritus professor at the University of Oxford, and I am going to talk about black holes, singularities, and cyclic cosmology. In all my pictures, as I try to indicate, time is going up the picture, so you have to imagine at the bottom is the Big Bang with the great explosion which creates the universe. Does it have to be this very special, singular, regular situation that the theories that people use, the models that cosmologists all use, assume exact symmetry? What happens if you have a general situation with all sorts of irregularities? According to the Einstein equations, the Ricci curvature is what's created by the matter, and the Weyl curvature is what is the free gravity. So the gravitational field is described by this Weyl curvature, and the matter is described by the Ricci curvature. Now, the Ricci curvature is a sort of regular inwards focusing in all directions, whereas the Weyl curvature gives you this great distortion. And what seems to be the case is that in the remote future, one has a dominating Weyl curvature, whereas the Weyl curvature seems not to be present in the very early universe. Here we have two of the most famous formulae of 20th century physics. There's Einstein's E equals mc squared, of course, and also Max Planck's E equals h nu. Max Planck's formula tells us that energy and frequency are equivalent. Einstein's formula tells us that energy and mass are equivalent. Put the two together, that tells you mass and frequency are equivalent. So when you have mass, you have automatically a frequency. So every mass is a clock. So when you want to bring clocks in, the rate of time, that's what mass does for you. If you have no mass, you wouldn't have clocks. When you don't have any scale, you can consider a kind of geometry which is called conformal geometry. Conformal geometry is the geometry of small shapes, if you like, of angles. And here we have a lovely picture due to the Dutch artist M.C. Escher, where he shows with a certain type of geometry. It's called hyperbolic geometry. Don't worry about that. But the important thing about this geometry is that you can represent infinity. This circular boundary to this picture represents the infinity of these creatures. So if they were photons, the photons could probe the boundary and go right through and seem to explore some world outside infinity. Very strange idea, but if there were no mass, that's the sort of picture which makes sense. Here we have a picture of the universe in its expansion. The remote future is this exponential expansion where this dark energy or cosmological constant seems to dominate, and we have the Big Bang at the bottom of the picture. And the feature of this is we can apply the trick that Escher used in his picture and squash down infinity and make it into a finite boundary. If you only have photons running around, then they won't notice the difference, and you can squash it down into a finite boundary. What about the Big Bang? Well, the idea is you can stretch that out into a finite boundary as well. You might worry, well, there's a lot of massive particles running around at the Big Bang, so surely they know how big the universe is. No, they don't really, because it's so hot, so dense and so hot at the Big Bang that they rush around so fast that the mass of particles becomes completely irrelevant. What about the Big Bang? Maybe you can imagine that extends backwards into something else. So this was the picture that modifying Paul Todd's idea into one where the Weyl curvature is actually zero at the beginning and not just finite as he had. You can imagine that this Big Bang was actually the continuation of something before. So I'm saying that why the Big Bang was so special was because it is the conformal continuation of something, the remote future. You stretch out the Big Bang, and then it becomes the continuation of the remote future of a previous eon. So in this picture, what we used to think is the entire universe, the Big Bang being the beginning and the remote future being the end, I'm saying that this is just one eon, one stage of a perhaps infinite succession of eons, one after the other.
So,
Shout out.
if anybody would do it, that creative motherfucker would.
Yeah, he's one of the major proponents of this sort of cyclical universe theory, and the article here that it kind of talks about this or summarizes this is titled "The Universe is Already in Its Sixth and Final Era."
And this is on Big Think?
BigThink.com, yeah.
Who wrote the article?
The person that wrote the article is Ethan Siegel. I'll go ahead and post it.
Siegel?
Yeah, nailed it. And the key takeaways are that from cosmic inflation to primordial particle soup, and the cooling aftermath, I'm going to paraphrase just to kind of skip through it. About 6 billion years ago, there was a new form of energy that began to dominate the universe's expansion, dark energy, which now, apparently, according to cosmologists, determines our cosmic fate. The era we're living in, where dark energy dominates the universe's expansion, is the final one, and the final one that our universe will ever experience. And they say that we're living in the end times.
Ooh. That sounds a little salacious. Sounds like a headline for the article.
Oh, it's beautifully said. Well, I mean, the headline grabbed me. Great job, Ethan. Just the idea is that.
What's the synopsis?
The synopsis of this is that we've gone through universal cycles, and we're on our final one because we really can't answer the question of cosmic inflation. That's kind of been the theme about this topic. Is I wasn't aware of this. Maybe some listeners are, but physicists are still trying to figure out what the whole, how would you say, the point of cosmic inflation is.
Right.
Yeah.
Right. And I mean, cosmic inflation was one of these things that really was nobody really even considered before.
Recently discovered too.
Right. Because Einstein, of course, Einstein's biggest blunder was adding in the cosmological constant to create a static universe, because he realized that there was some error, I think, without having that constant in there to make the universe static.
Yeah. Can we expand on that? Because you can
expand if you know.
Right. Sure. Okay. Yeah. So from my understanding, Einstein worked in the Minkowski space-time manifold, where it was assumed to be flat.
Ah, okay.
Right. And then in the sort of de Sitter space, where it's more apparently the manifold there, or the space geometry there, is more allows curvature and inhomogeneity. So, and I think Yeah, we'll get more to that later, but for the most part, the synopsis still extends to basically Einstein just being like, yeah, the universe is static.
Yeah. So he added in that parameter. It was a little presumptuous, why Einstein calls it a blunder.
Yeah.
Because he assumed a static universe without really much evidence. But then they realized that, the universe actually is expanding. So the cosmological constant is still useful because I think it controls the rate of expansion. Asterisks on that, but I think that's what it is. I haven't actually done the equations or the math to know for sure, but I think that's what it does. And yeah, so it's kind of weird. And what cosmic expansion or inflation actually is it's literally space is expanding constantly, and actually it's expanding faster than the speed of light, quote unquote. And what the consequences of that is, like, you'll get things like redshifting. So, when we look back in time through telescopes, as time goes on, the galaxies around us will actually become redder and redder because as space expands, it's actually stretching out those photons of light as time goes on. And that makes things more red.
Yeah,
and
that's increasing energy. That's decreasing energy, right? Redshifting.
I guess it is.
Right?
It's lowering the energy, right?
Yeah,
Because a longer wavelength means
lower energy, right? A longer wavelength. It's inverse with frequency, right?
Yeah, so a larger wavelength means a lower frequency, right? And then, of course, we know energy is proportional to h nu, with nu being frequency and h being Planck's constant. So as the wavelength increases, the nu decreases, which means your energy lowers.
Yeah.
So yeah, so actually I guess it is like you're losing energy in some sense. And actually, I don't want to get into too much, but there are some conservation law issues potentially with cosmic expansion.
Right.
But I'll let you continue on.
No, yeah, I mean that leads. I mean that great, fucking subtly put, because I mean this expansion affects radiation, matter, neutrinos, dark energy. They all change as a function of the space itself expanding. The temperature of the universe, like, this has consequences for that, and this is kind of where physicists are like, well, we're gonna suffer a cold, lifeless death because, well, everything.
Physicists always so positive.
Yeah. Well, I mean, like what you're saying, right? It's because of the relationship that you just mentioned, the universe would have the big freeze, as some people would call it. Entropy would essentially maximize, and order would decrease, and you would essentially
hit this equilibrium point where all matter and energy is dispersed evenly throughout space.
Yes. And that's assuming that space-time is flat and it's just expanding outward. However, this paper argues that there are 6 different eras that we can break the universe into, and apparently we're living in the final one. And
now, is this still accepted physics, or is this in the realm of aeons yet?
This is in the realm of. This is sort of the prerequisite to all of this, to talk about.
This is accepted physics. You're talking about the eras of the Big Bang, like the timeline of the universe is what you're saying.
Right.
Okay,
right.
yeah. You've seen the picture. It's like the picture of the tube, and then it shows like the instant of the Big Bang, and then it's like these other eras, like the recombination epoch or something, and then the whatever. You've seen it probably. The image.
Yeah, the idea here is that we're functioning off of knowledge that, I mean, things that we know. Like, for instance, the question about matter is that matter dilutes as the universe expands. Does that make sense?
Yes. Well, it's not diluting, but the density, the matter density, gets lower.
Yeah, exactly.
Because your matter gets spread out. The same finite amount of matter gets spread out over a larger volume, which means density decreases.
And the same thing with radiation. So we're talking about energy in the form of like electromagnetic radiation, like light and photons and stuff like that.
Right.
The density decreases as the expansion rate remains constant. However, the one interesting thing is the energy density of dark energy does not change.
Oh, interesting.
Yeah, the according to cosmologists, dark energy density remains constant. Okay, this is what I want to get to. The different eras that we see or that we talk about in the 6 eras and the final eras or whatever. The first era is the inflationary era, which preceded and set up the Big Bang as we know it.
Preceded.
Yeah.
Before it.
Yes.
Okay, so this is getting into the actual conformal cyclic cosmology theory.
Yes, it's
Okay.
I'm laying some of the bedrock here.
Gotcha. Okay.
And then the second era is a primordial soup era.
Now this is accepted physics.
Yes.
Yes.
From the start of the Big Bang until the final transformative nuclear and particle interactions that occur in the universe that generate galaxies and shit.
Right.
And then we get to the plasma era from the end of non-scattering nuclear and particle interactions until the universe cools enough to stably form the periodic table, and we get all the elements. And then there's the Dark Ages era, from the formation of neutral matter until first stars and galaxies reionize the intergalactic medium, whatever that means. I'm not a cosmologist, so the Dark Ages makes the least sense to me.
Yeah. Same.
Yeah. So if you're a cosmologist, please explain the Dark Ages, and we'll pin it for everybody. But the Stellar Era is the end of reionization until gravity-driven formation and growth of large-scale structures ceases, when dark energy density dominates over the matter density. And then we're in the final era. Apparently we're in the Stellar Era, or close to it. At least is what this paper argues.
The final era almost sounds a little bit disingenuous.
The final era is the dark energy era, let me just say.
Okay.
And that's the final stage of our universe, where the expansion accelerates and disconnected objects speed irrevocably and irreversibly away from one another.
That final era sounds a little bit disingenuous to me, though, because another massive caveat. I'm not really sure. I'm not a cosmologist, so I don't know what the simulations predict, like all the way to the end of the universe. But it's like we don't really know if there's going to be another classification after this, or at least I don't know. Maybe there is something, but is it really the final, or is it just the current era?
Well, I think finding our place, it might be somewhere in between, because we still don't know. I don't think we still have enough information about which era we're solidified in, because we've just discovered dark
matter.
Yeah.
Yeah, that's what I'm saying. I'm like, can we really even say that? But then again, I know cosmologists, of course, like physics has a much deeper like standard of evidence and everything. So maybe they know a lot of shit about dark matter, just not actually like found the particle yet. But maybe they've done enough simulations and things where they know that this will be the final era that has any meaning of classification before the end of the universe, let's say.
Right. Because for those of you not in the know, as physicists, we model everything based on current information.
Yeah.
Yeah. So we're taking as much data and then inputting
sometimes
into the model, huh? What do you mean?
Well, I guess it's always still based on current information, but sometimes you can extrapolate things and add certain parameters into your model,
right? And that's
to see
what
if it will fit. Yeah.
Right. That's what we're trying to do, in a sense, like seeing what happens, and our current models show the extrapolation.
Right.
That
and sometimes they're really good fits, and then sometimes they're okay fits, and sometimes they're kind of poor fits.
Yeah.
But I do know we have things like the cosmic background power spectrum and things like that from WMAP that kind of show the beginning radiation. It's like literally like a map of radiation of the early universe that give us a lot of tools and a lot of kind of guidance to actually run certain simulations on how the universe should actually unfold.
That's fascinating.
Yeah. It was a huge feat for, cosmologists, I mean, because it was such a, instrumental part of actually having some kind of experimental an experimental roadmap, I guess you could say, of how the early universe formed.
Right.
So we do have that, at least.
Right. Damn, I forgot about that, because the most famous radiation that you hear about is the CMB, the cosmic microwave background. But they're saying, but in the CMB, they're saying you see fingerprints of the early universe.
Yeah.
Interesting.
Yeah, the CMB I think is rife with a lot of information that maybe not even tapped out fully yet. I keep seeing new things and new interpretations and people still using the CMB in their research to kind of come to new conclusions, including Penrose on this CCC theory.
If these signals are light signals, if they, more importantly, are gravitational signals, they can get through. And I thought about if you have collapse, if you have black holes which spiral into each other and huge galactic scale black holes. I'm not talking about the ones that LIGO sees, and we certainly see black holes running into each other, but the black holes at centers of galaxies, absolutely enormous ones, eventually will start to spiral into each other and produce signals which maybe we could see. There are also other effects which we can see, and it seems to be the case that there are signals that we are seeing in the early cosmic microwave background which are explicable, and only explicable as far as I can see, in terms of something going on before the Big Bang, which is consistent with the picture which I've just been showing you.
Yeah. Let's. So now
I don't know if it's jumping the gun. Maybe we should actually explain the CCC first. I feel like we're kind of putting the cart before the horse, right? Because people are like, "What the fuck are you guys talking about?" Like, what is it exactly?
Okay, the CCC. Let me go ahead and summarize it.
We should give a summary.
Let me give you a summary. The hypothesis raised by Penrose. This is an article that really helped me summarize it. Metaphysical Exile. We'll go ahead and put the links. I'll go ahead and source the stuff down there. But the gist of CCC is basically, number one, the most advanced observations we have of the universe made via satellites is the WMAP.
Yeah.
Or WMAP. With other instruments that measure the background radiation left by the Big Bang indicate that the universe will continue to expand faster and eternally. Cosmologists and physicists in general attribute the expansion to the influence of dark energy, which slowly but surely expands the very fabric of space-time. Number two, the expansion won't be extreme enough in order to produce a scenario known as the Big Rip, which is when all the most elementary particles and even space-time itself are ripped apart due to the ever-increasing acceleration of the expansion. That is something that most people, it's not intuitive to a lot of people, that the Big Rip would even be a thing.
Yeah.
But the argument, I don't know, do you have a good summary? You're usually pretty good about summarizing.
They said it's not enough speed, or it could be, or it is enough speed.
They're saying that the expansion is not extreme enough to produce the Big Rip.
Okay. So then what I would imagine is it's some kind of weird analogy. I can't really summarize it because I don't know it and I didn't look into it. But what I would imagine is they're talking about that somehow the acceleration of space becomes so fast that eventually that the matter and things that are inside of it will be pulled apart, by just the matter of space moving away so fast. Because as we already mentioned, space already can move technically, or expand faster than the speed of light in some sense.
So is it better to think about space as like let's say your atoms in space? We've already done experiments where they measure time dilation in an atom. Like you just recently told me, they measure time dilation.
Yeah.
From an atom on the top of the atom to like
the bottom of the atom. Yeah.
Insane.
Or a collection of atoms, I should say.
But to me, then that gives the picture that atoms are sort of locked in place. It's sort of like an image.
Okay.
Where the image is in two dimensions. I'm giving a very rudimentary picture, people, so please just kind of use this as an analogy for now. But how I see atoms locked into space, to give a picture of what the Big Rip looks like, is you're essentially stretching that paper so far that it literally rips the paper, right?
Yeah, I think it's something along those lines. I can't say for sure because I don't know it, but I would imagine that has something to do with it. Because that paper, if you analogize paper to space, is being stretched, and it's being stretched infinitely and accelerating. So I imagine at a point there's just an acceleration enough to where it just rips apart. But I don't really know for sure. I don't really know.
We're not cosmologists.
This is an extreme, take it with a grain of salt moment.
But that's my take. I mean, just from the research that I've read, of how the atoms, how we measure time dilation between atoms and all this other stuff. It seems like you can sort of imagine that the matter that is in space is sort of locked into space, and gravitational effects influence in such a manner that the expansion of space overcomes the nuclear forces that are holding matter together. And
can you say that though?
I believe
maybe you shouldn't say that.
Okay, well let me.
But what you're saying sounds reasonable, but I don't know if you can make the claim of strong force, right? Maybe you can maybe it's not the strong force being overtaken. Like you're getting a little too specific.
Well, I'm saying the
without knowing for sure.
Right.
Yeah, maybe you could look up the definition. It might be succinct enough on Wikipedia. But I wouldn't say necessarily like strong force or anything until you really know, because it could just be electromagnetic force, right? And it could just be a plasma, or maybe we're just completely wrong.
Right. Well, here's the example though. Here's the author example from Wikipedia. Authors considered a hypothetical example in which case the Big Rip would happen approximately 22 billion years from the present. In the scenario, galaxies would first be separated.
Damn, so soon?
Yeah. About 60 million years before the Big Rip, galaxies would begin to disintegrate as gravity becomes too weak to hold them together. Planetary systems would become gravitationally unbound about 3 months before the Big Rip, and planets would fly off into the rapidly expanding universe. In the last minute, stars and planets would be torn apart, and the now dispersed atoms would be destroyed.
Okay, that's better. So it's actually not. So what you were saying was incorrect.
Okay.
Not the strong
force.
Well,
we'll edit that out for sure.
Yeah. So it has to do with the gravitational force becoming too weak. Why that is a little strange. I don't know why that would be.
Yeah, it says the now dispersed atoms would be destroyed about 10 to the 19 seconds before the end. And even space-time itself would be ripped apart. And the scale factor would be infinity.
I wonder how they would even come to that. Like, how could space get ripped apart? How would you even come to that conclusion?
According to the standard model of cosmology, the scale factor of the universe is accelerating, and in the future era, the cosmological constant dominance will increase exponentially.
Because the cosmological constant is changing?
Yeah, it's apparently dynamic. Yeah.
Really? I didn't know that.
Yeah.
Oh, so it's something probably within the Einstein field equation that shows that space-time will become...
it's untenable, bro.
I can't even speculate.
I
don't want to even say
this is
shit,
space.
I'm not a cosmologist.
Space shit, bro. Damn.
Yeah.
Well, the possibility of a sudden rip singularity occurs only for hypothetical sort of matter with implausible physical properties, according to the Big Rip picture here. Which is why a lot of people kind of hold that with a grain of salt, but that's essentially a synopsis of what the Big Rip is supposed to be.
So gravitational force becomes too weak to sustain the large, I guess, accumulations of matter like stars and planets,
right,
etc.
Exactly. Yeah.
Galaxies.
Yes. However, the acceleration and the expansion will produce another end of our universe, the scenario called heat death, which will occur when the entropy of the entire system reaches a maximum point and work can no longer be performed in the universe.
Now, heat death, I think, is regardless of a Big Rip or anything.
Right.
Because we know entropy is always increasing, so eventually there's a max entropy in theory, I guess. Mm-hmm. Not sure if that's even 100% certain, but I'm pretty sure it is.
Finite and what? Finite?
A max entropy.
There's a finiteness to it?
Yeah, because if you just think you want to carry everything out to its final state, right?
Yeah.
All stars eventually consume all of their energy, and then they eventually form black holes. Mm. Black holes, we know, radiate, and then eventually black holes will radiate until they evaporate, and then there's nothing left.
True.
And of course, black holes will also consume all the rest of the matter and stray photons and whatever. So I mean, it just logically follows that there has to be a max entropy in some sense. Mm-hmm. I don't know how else there couldn't be.
Yeah, true. Well, if that's not bleak enough for you, this is also. Let's go further. So other scenarios that could have been discarded by observations, at least for now, such as the Big Crunch, in which the mass of the universe will collapse in on itself, creating the same singularity as you would the Big Bang. That's the most intuitive one because, nature. We often see oscillatory motion in nature, and we're like,
which one is it? The Big what?
The Big Crunch.
Oh, right.
Yeah.
Right. So that's basically the inverse of cosmic expansion.
Right.
So cosmic expansion is always expanding outwards. The big crunch is like, oh, we're going right back to the singularity basically now.
Yeah.
The other direction.
Right. The collapse of the universe into a new singularity would occur only if we didn't have a force that produces and ever, we don't have the cosmology constant. We don't observe that, but we do. Which is...
So the big crunch is unlikely.
Right.
Right.
Yeah.
I think I've heard that. The big crunch is something that people don't think is...
Well, yeah, because
happen.
the cosmological constant changed it all.
Okay.
And number 3, they propose the heat death and maximum entropy will only occur after all stars in the universe go dark, becoming white dwarfs, black holes, or something else depending on their mass and composition. Physicists know that if the amount of dark energy in the expansion of the universe we currently observe remain about the same, the last active phenomena in the universe will be black holes.
Mm-hmm.
But even they will die after, like Terence was saying, they emit radiation and their lifetimes are finite before they evaporate via Hawking radiation. And the universe will enter its last and eternal phase, which is nothingness.
So nihilistic in the universe.
No, the final phase is fundamental particles and photons all moving in the speed of light in an empty and random void.
Mm-hmm.
And in this random void is where the CCC shines.
Right. It's all born out of Roger Penrose just being bored with the end of the universe.
Let there be light.
Right.
Is what he said.
Right. And it's actually, I was actually very impressed by it. And it was just such a clever thing to come up with.
Oh,
I love this idea that he has. It's really cool. Of course, to let the audience know, of course, I've heard counterpoints against it. And people don't think that it has some validity in some circles. But it's really interesting concept, and who knows, like maybe there are parts of it that could be true. And of course, I guess when we actually get into what CCC is at some point, maybe
we're edging. We're
30 minutes of the podcast.
What are we doing? We're like,
yeah, we're straight up intellectually edging people right now, as you were saying. I mean, this is next level. This is tantric shit right here.
Intellectual tantric. So when people accuse us of not getting to the point enough,
I get to the point always. This is your lead though. So
I like to edge you
this.
guys.
I'm gonna let you take this
like
credit.
this is foreplay to me. we're
So this is a good demo. I guess this means that Juan's the better lover probably. I just go straight to town.
straight. I just give it. Hey,
Juan likes to put the candles on, and
yeah, some of you don't appreciate the art of intellectual lovemaking. Okay, no, but in all seriousness, the fourth point is, which we've teased. Mm-hmm. Penrose and his colleagues assume in the extreme future that, when the elementary particles decay, including protons, he assumes that black holes, this is already assumed, but black holes destroy all the information, or they scramble the information.
Because they don't destroy any information. Well, I guess they
scramble states. Yeah, let's not get into that. But essentially,
it's tough.
That's more quantum information meets gravity and whatnot.
Entropy stuff and all that.
Yeah. But essentially, we need to know this because this is the beginning of his CCC theory. However, if these two conditions hold, the only things left in the universe after the evaporation of the last black holes will be photons and other elementary particles without mass. And here's where the CCC hypothesis comes into play, because he talks about geometrical conformity. And in physics, time needs objects with mass to have any meaning. A universe composed only by photons and massless particles becomes invariant relative to its size, regardless of how big it was before. It stops being infinitely large and becomes infinitely small, since without any way to measure time, there is no space. All of a sudden, all particles and photons that were left in the universe occupy an immensely small space, just like the Big Bang that produced our universe.
damn, you kind of flew through that. Like, there's a lot of shit to really digest. There's
kind
some
of unpack,
concepts in
yeah.
there that I had to think about for at least like 15 minutes.
Yeah, let's try to unpack that because you're totally right.
Maybe should we just watch maybe
Should
the
we pull up
Penrose
the video?
because the Lex
Yeah.
video is really great.
Okay, perfect.
I mean, from straight from the horse's mouth. Man.
perfect
It's-
transition. Yeah.
Yeah.
Let's do it.
So I'm sure you didn't get anything of what the hell Juan was saying there. So just watch Lex Fridman's clip.
Yeah, I mean, okay. Let me
a
just
superior
let me,
podcast to ours, and
right.
you
Let
can
me
see
just
what it is.
let me help you digest this. Essentially, after black holes have all evaporated, he's saying that all you're left with is massless particles, photons, just traversing through space. But the argument is that if we're talking about space and time, there's no mass in this,
Right.
right?
There's no mass eventually because all of the mass gets eaten by black holes. It evaporates, and eventually it's just photons just racing to the edge of the universe. But then the real clever shit to me is the whole conformal mapping. To now where he makes the argument of how the definition of scale is lost. And eventually that definition of scale being lost because it's contained, the definition of scale resides within matter. He'll explain it in the video.
Yeah.
And then eventually it's like you're basically recreating the universe again because of this scale invariance between the end of the universe and the beginning of the universe.
Well put.
If you don't understand this, you'll be able to think about it again
Yeah.
with this video.
Yeah,
So
well,
just
well
watch.
put. But that's a good synopsis. Here we go.
The universe is actually undergoing this exponential expansion. So it's a self-similar expansion. And it seems to be a feature of this term that Einstein introduced into his cosmology for the wrong reason. He wanted a universe that was static. He put this new term into his cosmology to make it make sense. It's called the cosmological constant. And then when he got convinced that the universe had a Big Bang, he retracted it, complaining that this was his greatest blunder. The trouble is it wasn't a blunder, it was actually right. Very ironic. And so the universe seems to be behaving with this cosmological constant. Okay, so this universe is expanding and expanding. What's going to happen in the future? Well, it gets more and more boring for a while. What's the most interesting thing in the universe? Well, there's black holes. The black holes more or less gulp down entire clusters of galaxies. Who's going to be bored by this universe? Not us. We won't be around. It'll be mostly photons running around. And what do photons do? They don't get bored because it's part of relativity, you see. It's not really that they don't experience anything. That's not the point. That photons get right out to infinity without experience any time. It's the way relativity works. And this was part of what I used to do in my old days when I was looking at gravitational radiation and how things behaved in infinity. Infinity is just like another place. You can squash it down as long as you don't have any mass in the world. Infinity is just another place. The photons get there. The gravitons get there. What do they get? They run to infinity. They say, well, now I'm here. There's something on the other side, is there? The usual view, it's just a mathematical notion. There's nothing on the other side. That's just the boundary of it. A nice example is this beautiful series of pictures by the Dutch artist M.C. Escher. You may know them. The one's called Circle Limits. They're a very famous one with the angels and the devils. And you can see them crowding and crowding and crowding up to the edge. Now, the kind of geometry that these angels and devils inhabit, that's their infinity. But from our perspective, infinity is just a place. And their infinity, by this nice transformation, you squash their infinity down so you can draw it as this nice circle boundary to their universe. Now, from our outside perspective, we can see their infinity as this boundary. Now, what I'm saying is that it's very like that. The infinity that we might experience like those angels and devils in their world can be thought of as a boundary. The remote future, on the other side, I'm claiming is that, where do the photons go? They go into the next Big Bang. You've got to get your mind around that crazy idea.
Taking a step on the other side of the place that is infinity. Okay,
Yes.
but...
So I'm saying the other side of our Big Bang, now I'm going back into the Big Bang.
Backwards.
There was the remote future of a previous eon.
Previous eon.
And what I'm saying is that previous eon, there are signals coming through to us which we can see and which we do see. And these are both signals. The two main signals are to do with black holes. One of them is the collisions between black holes, and as they spiral into each other, they release a lot of energy in the form of gravitational waves. Those gravitational waves get through in a certain form into the next eon.
That's fascinating that there's some, I mean, maybe you can correct me if I'm wrong, but that means that some information can travel
Yes,
from another eon.
exactly.
That is fascinating. I mean, I've seen somewhere described sort of the discussion of the Fermi paradox. You know, that if there's intelligent life,
Yes.
being, you know, communication immediately takes you there. So
We have
do
a
you think-
paper. I have my colleague Vahir Gurzajan, who I worked with on these ideas for a while. We have a crazy paper on that. Yes.
So
Looking at the Fermi paradox. Yes.
right. So if the universes are just cycling over and over and over, punctuated by
Yep.
punctuated the singularity of the Big Bang,
Yes.
and then intelligent or any kind of intelligent systems can communicate through from eon to eon. Why haven't we heard anything from our alien friends?
Because we don't know how to look.
That's fundamentally the reason. Because
I don't know. You see, it's speculation.
Pretty great synopsis, huh?
Yeah.
If you would, if you still didn't understand it, I would watch that video as well again, just to really try to drive the point home.
Before Lex started bringing aliens into the conversation.
Right. So yeah, it's It's very interesting theory, and immediately though, what came to my mind, I wish we had Penrose on the podcast because I had 3 questions I wanted to ask him about it.
Mm-hmm.
So 3 issues that immediately came to my mind that I would like to tamp down, and I don't think we're going to be able to answer them in this podcast. Maybe we can just discuss, maybe.
Yeah.
But the first one, that's actually a new issue. Just thinking about the big rip that we were discussing before, is Penrose discusses these infinities. This boundary of infinity, basically. And I guess just as an aside for the affinity, people who want to try to understand this better, like how can you make a boundary for infinity? How does that make any sense? One of the things that first came to my mind was solving the Gaussian integral in Cartesian coordinates. When you solve the Gaussian e to the negative x squared in Cartesian coordinates, you actually have to do this trick. Or one of the ways you can solve it is you do this trick to change it into spherical coordinates. So when you go from negative infinity to infinity, or it's like negative r to r for the radius, and you're like, what the fuck? And then when you change it to spherical, you suddenly have this spherical surface now where you can actually integrate over the Gaussian and you get this finite answer.
Right.
So maybe that could help you if you have trouble trying to understand a boundary of an infinity. That helped me a little bit try to internalize it. So the Gaussian from Cartesian to spherical coordinates. Solve that integral. Anyway, but the point was, so when he says,
what's the infinity part of that Gaussian?
It's the actual
The
the boundaries. The boundaries.
How
of
it scales, how the boundaries can scale? That's what you mean?
Well, the boundaries go from negative r to r.
In Cartesian.
Yes.
Yeah.
Or yeah, for the radius, and the r value those r's go from negative infinity to positive infinity.
Right. Okay.
Remember?
Yeah.
Yeah. To get a finite answer from the Gaussian, and it ends up being like square root of pi or something. I don't know. I forget what it is.
Yeah.
That might be wrong, so don't take that as the answer. There could be like a factor of 1/2 or something there. But yeah. So anyway, what was I saying? Yeah. So the first problem I had with that was he's talking about the boundary of infinity. So you never actually cross over that boundary, from what I'm understanding.
Right.
I don't know, because you can't really cross over infinity, right? You're always contained within the boundary. So that's just one misconception to tamp down. But then that leads me to the question of the big rip. So then if the boundary is still always, or infinity is always still kind of expanding in some sense.
Well, the best way I could think about this is infinity and periodicity are, I think he's using this in a synonymous way, because the periodicity in the pattern is what he's arguing space-time is. And I think I'm going to show a video that will probably help elucidate this.
Okay, but yeah, I'm just saying that if space-time is expanding still, and it's constantly expanding, because this whole scenario of the conformal cyclic cosmology framework, the universe is just always expanding. And if we know that the cosmological constant says the universe is always accelerating, eventually it's just like after a certain point, the universe is going to be a run amok with acceleration. Like it's just going to be absurd, the acceleration. So to me, that's one problem. It's like, how does that square away with the same kind of universe that we operate in? Because to me, that would just be like, it would seem like it's untenable at that point. And maybe the big rip would be almost inevitable in that kind of framework. Because if the universe is always accelerating, then it's just getting faster and faster and faster and faster till where it's like inconceivably fast. So that's my first gripe. My second gripe has to do with photons. So the photons are supposed to be at the edge of the universe, right? So then, of course...
they reach the boundary.
They reach the boundary, right. So then, of course, what we think of in this scenario, when you lose your scale, right, we can almost think of it as like, imagine it as like a fractal, right? When you look at the Mandelbrot set, the more as you zoom in, you eventually come into another Mandelbrot. So it's like, with this one, we're starting with the Big Bang, and then we zoom back in, and we get to another Mandelbrot. But now it's like, instead of the photon, let's imagine a photon is now the entire new universe. So what I was thinking was...
That's the argument, though. The infinite recursion, yeah.
That's what I think. That's what I'm trying to figure out, though, exactly what he's trying to say. Because is he saying that this singular photon is now the new Big Bang? Because that, to me, then indicates that a photon needs to decay. Because then what happens is you're saying that basically a photon needs to decay into all particles and matter again to create this new universe. So I'm thinking, is he saying that basically we don't know, because we don't really know if a photon can decay, right? And I actually looked this up. The upper limit of photon decay is like something like 10 to the 18th years. So if the photon could decay, then the upper limit is like something like 10 to the 18th years for the time scale. So I'm thinking, is he saying that now this new photon is basically the start of the new universe, and now this decays into, I guess, the new versions of protons and neutrons and all that stuff, and this is just, the cycle continues and continues? That's my second gripe. And then my third gripe is, so Calabi-Yau manifolds. So,
right.
Oh, that's not really a gripe, but I guess my thing was, I immediately just thought I wonder if this actually, this must be, this would rule out string theory, or this is not compatible with string theory. Because, in string theory, we have these curled up dimensions, right? So I was trying to think about how does scale really matter? Because in this kind of universe, almost like, it's like when you do this rescaling of the beginning to the end, you're still kind of like, it's almost like you're getting smaller and smaller in some weird way, right? Mm-hmm. Smaller, quote unquote.
Right.
Like if we try to conceive of it in our human scope. Mm-hmm. So then I'm like, does scale actually matter, though? I'm trying to think of it in an instance of, like, does the universe have this kind of intrinsic property where scale always will matter, even though Penrose says it does not, because matter is what keeps the scale information?
Yes.
But I'm thinking, is that actually true? So then I was trying to think of some things that might interfere with that, and the first thing I thought of was string theory and Calabi-Yau manifolds. So the Calabi-Yau manifolds are what they use, I believe, put an asterisk on this, I think it's true though, is what they use to make the curled up dimensions for string theory. And these are on the order of, like, the Planck scale, or maybe below, I think. Another asterisk. It's really small, though. It's small enough to where we can't see them. But then I was thinking that if that's true, then that means that at a certain point, if curled up dimensions exist, if our universe was 10-dimensional or something along these lines, then that means that these photons we would actually start to see 10 dimensions, and dimensionality would actually become more and more visible as these transitions to these new big bangs would happen.
Right.
You see what I mean? Like, we see 3 dimensions now, but if this kind of CCC universe existed, then this means that the 10-dimensionality would become more and more significant, and then scale would matter because it's a property of space-time.
Interesting.
So those were just the 3 gripes that I had just immediately off the bat that I would like to clarify with Penrose, but I don't know. I'm sure I don't know if we'll ever get that opportunity, but those are just the 3 thoughts that came to my mind. Did anything come to your mind in terms of that?
Yeah, I mean, I started thinking about. So for the record, I'm putting bits and pieces. I will be producing this episode, so I will definitely be putting more information for the listeners so that they can get a more complete picture.
Mm-hmm.
And I hope that we've given a complete picture. But I have seen this talk live. I saw him
Oh, really?
in 2015, yeah. And when he
Damn.
was giving the talk, and I should have asked him questions, but
If only we were a podcast back then.
right. Well, he what I did find interesting is he's proposing a sort of linearity to the universe. Like he's saying, like in the cyclical theory, he has a linear mapping, and if I will do myself some favors.
Is that where he draws the tubes?
Yeah. He draws a
Yeah,
sequence of tubes
Couldn't quite understand.
in sort of a linear fashion where the implication is that, well, a part of his theory that I did appreciate was that he's trying to make it testable. He was saying that, because we have this linearity and this overlap, you might have some boundary overlap where you see ripples of
Gravitational waves specifically
Yeah.
he used. Yeah, it's pretty cool, the experiment, because he showed that you can somehow look at these the CMB power spectrum to look at these like ripples in the CMB, and he showed that there's actually like potentially some evidence for it. I don't know how strong the evidence is.
Well, I'll get to that, but
Yeah, but I know he says like 99.98 or something, but I don't know really how true that is. Because it could be a qualitative issue, right?
right.
But pretty cool.
Yeah, he does give some evidence, although it might be sort of untenable. Some people are saying
It's just not enough to convince me yet. But
Right.
it's always great to try to come up with something, right?
right. Well, I appreciate his approach, but basically that's kind of the five. How would you say? The 5 points to kind of summarize CCC.
5?
Yeah, that we went through.
We went through 5?
Yeah.
Oh. Well, I'm glad you know, because it wasn't ever in my mind.
Well, just how the last process is like, it's basically the black hole stripping all the information. All that's left is photons, and then photons go through space and begin the cycle process of the Big Bang.
So it's like CCC combined with modern accepted physical interpretations of cosmology.
Right.
Because really the only CCC part is in the beginning and the end.
Yeah. What was interesting to me is that he makes the argument that existence for photons is kind of mind-numbing because they are infinity in some ways.
Mm-hmm.
I mean, you say that the physicists think that the lifetime of photons is 10 to the 18th.
No.
Is that an observation or is that a...
No, this is just a calculation for the maximum lifetime if a photon could decay. At current state, we don't believe photons decay because they're massless particles. Mm-hmm. So I think what the thing they were saying is for a photon to decay, it has to be a massive particle. Mm-hmm. So, of course, we think of photons as massless, but there were upper limits put on these things. Like, I think they said the photon would have to weigh like 10 to the negative 54 kilograms or something to be able to decay into a mass. And then that would last for 10 to the 18th years. But, of course, if you're a massive particle, then you also don't experience time, as Penrose is saying, as a photon is created and ends its lifetime at infinity and the beginning of the universe all in one instant, basically.
Right.
So if a photon's massive, then it reaches like 9.99999 percent the speed of light, and then eventually, it's like, I think the calculation was it would take 3 years in a photon's lifetime to reach the end of the universe or something.
Insane.
But then for us, that would look like 10 to the 18th years.
Fucking insane.
But this is just me thinking, like, I looked this up just thinking like, can photons decay? Because I was trying to figure out, like,
That's
how
a
does
good
the
question.
actual Big Bang moment happen, right?
Right.
Because we have to reproduce all that matter again, right? And
Yeah.
Penrose never really talks about that part. He just says there's photons at the edge, but he doesn't tell about the actual, like, Big Bang moment when the universe is recreated again.
Right, and this is where I found it lacking, and so this is why I want to talk about more flesh out what I think he's trying to convey in his CCC theory. He briefly discusses quantum fluctuations, but he kind of brushes it off, I guess, because he presumes that we kind of understand the current model, I guess, of how we imagine the Big Bang to be.
Yeah, okay.
Like being born out of quantum fluctuations.
Yeah.
Yeah. And to kind of give some people background into this, let's go ahead and pull the other video up here.
Is Princeton University's Professor Richard Gott.
These are closed time-like curves. It's time travel to the past. These are general relativity solutions that are sufficiently twisted that they allow the time traveler to circle back and visit an event in his own past. So this started out when I found an exact solution to Einstein's field equations for a cosmic string. Cosmic string is a thin piece of vacuum energy left over from the Big Bang. It has a negative pressure along the direction of the string and a positive energy density. And this is like when the vacuum decays, it's like snow melting and you're left with a few snowmen standing. And we're looking for these. We haven't found them yet, but they're predicted in many theories. When the strings move fast enough, but still slower than the speed of light, but close to the speed of light, you could circle them and come back to an event in your own past. So this was a time travel solution. Like a number of time travel solutions in general relativity, there was originally Kurt Gödel found a rotating universe that had closed time-like curves like this in it. And Kip Thorne and his collaborators Morris and Yurtsever found time travel solutions with a wormhole, just flat space-time. Time is going this way, space is going this way. And here's my world line. I'm going straight up here toward the future. I'm just staying home, okay? But this space-time could be twisted around like this so that my world line always is going toward the future, toward the future, toward the future, and yet circles back and visits the past. This is just like what happened when Magellan's crew went west, west, west around the world and found itself back in Europe. So if you're a time traveler like this, you're always going toward the future. But like a loop-the-loop on the roller coaster, you're finding yourself looping back into the past because space-time is curved.
So a closed time-like curve can allow time travel to the past. But in order to understand how this relates to the universe creating itself, one needs to understand the history of the early universe. According to most cosmologists, the universe underwent an exponentially fast expansion known as inflation. This was first described by Alan Guth, who we interviewed in episode 4 of this series.
The overall effect was gravitationally repulsive, and this explained like how the universe started expansion, and also explained how the microwave background radiation was so uniform because there's a little extra time in there for different regions to get in causal contact. But Guth wanted this vacuum state to decay into normal particles, so we'd have a normal expanding Big Bang model. And so he wanted this to decay all at once, so it would be uniform. And that's like putting on water on the stove and having it just turn into steam all at once. But he realized that there was a problem with that, and that was that when you actually would do that, it would form bubbles of steam, just like when you boil water. I wrote a paper in 1982 saying the answer to this problem was that we lived in one of the bubbles. We lived in a bubble universe. Our universe was one of these bubbles. And from inside the bubble, everything looked uniform. And so that solved Guth's problem. Beyond our universe, we expect to find other bubble universes. And within a very short time after my paper appeared, a paper by Linde and Albrecht and Steinhardt appeared that had a detailed particle physics scenario to produce this. And this was called new inflation, and it solved the problems in inflation. So this was a geometrical picture of having a multiverse. So we believe in inflation because it explains so beautifully the fluctuations that we see in the cosmic microwave background. This looks like something Dr. Seuss would invent. This is inflation, and Linde said that inflating universes could give birth to other inflating universes by quantum fluctuations. This was like branches coming off a tree. What Li-Jing and I proposed was that the universe could give birth to a branch like this that circled back in time, like these time loops, and gave birth to itself. So there's this time loop at the beginning, and this universe gives birth to itself. The great thing about inflation is that a little tiny inflating piece grows up to be an enormous inflating piece, each little bit of which is exactly like the little bit that it started with. So what if one of those little bits was actually the bit that it started with? Then it could give birth to itself. Something funny had to happen at the beginning of the universe, and time travel and solutions in general relativity seem supremely suited for the purpose. Many people today believe that we live in a multiverse with like the many bubble universes. Why do they believe that? Well, because we believe in inflation. Because it does things we can test, like the cosmic microwave background, the fact that we're seeing inflation occurring today. Inflation is testable. These early universe models will be tested if we get the string theory to finally produce what we call the theory of everything that we're looking for. The important thing about that theory is that it has these extra tiny dimensions that are curled up and tiny. Well, inflation tells us that the big spatial dimensions that we see today, the three big, large spatial dimensions, they were tiny. Here, all the spatial dimensions are curled up and tiny in the early universe. And ours just goes one step further. There's a curled up dimension of time here. So this seems to fit in very well with what superstring theory might produce. And I think ultimately, when we get a theory of quantum gravity, there'll be other testable predictions it makes, and then you'll look at the solutions of those equations in the early universe, and you'll see if you get a model like this.
That was it.
That was rough.
Don't you love
wow,
that guy?
Doug Dibidom's goofy cousin is just going off.
Don't you love it? That guy, he's a treasure to me. Works at Princeton.
That turquoise suit with the brown hat, green tie combo. What a choice. What a fashion statement.
I love him. Imagine having him as a professor.
I don't think I could do it. I couldn't make it.
I think y'all would get along.
I was fighting back the sleep, man.
Oh, I see. Well,
like this man is going off on Pope Francis. I don't know what the fuck he's talking about. You might have to recap some of that because I was lost for a majority of the time.
I played the episode only to save myself some production stuff. But essentially, what the professor was saying here was kind of outlining a competing model of what the cyclical universe looks like, and sort of the recursive nature of it. What he's saying is at the beginning of the universe, I think this helps highlight something that a lot of the infinite regress that we get when we talk about the Big Bang, his sort of space-time model has a built-in periodicity to it, meaning that like you see how it curls up the manifold picture that he had curled in on itself to imply the periodicity of his space-time. And there's a possibility. I'm not going to play it. Well, maybe
he kept showing a picture of some like crazy looking trumpet. I didn't know what that was.
Right. Yeah. Well, that's his picture of the space-time curvature here. I don't want to skip around too much. to make it easier for me to edit for myself. But let me see. Maybe I can
one
skip
more
ahead.
edit.
Yeah, I guess I can.
Damn, that voice too, man. If you imagine. I thought you picked that as a meme.
No, the guy knows this. He's from Princeton. He knows this shit.
Damn, well, I'm glad you can follow it.
Okay.
There were so many factors I couldn't get over.
Okay. Well, here's the part that I think is relevant here to kind of elucidate the picture more. Let me
All right.
see.
Measurements of time and space become uncertain. The time interval between two events becomes uncertain, and the spatial separation between two events becomes uncertain by the uncertainty principle. So closed time-like curves would naturally seem to occur. This is called space-time foam, and it's multiply connected, like we want, multiply connected with all sorts of bridges going different places in time and different places in space. It's always pictured as a sponge. You know, this is how space-time looks at that microscopic scale. So that's why I said that.
Another model that takes advantage of quantum uncertainty is Vilenkin's tunneling from nothing, where space and time tunnel into existence from a state of no space and time. This tiny patch of space-time may have its negative gravitational energy balance its positive mass energy, and so could exist forever, inflating into the universe that we see today.
Sound.
It's like that meme sound.
Tunneling, quantum tunneling, by definition, has two ends. There has to be a classical solution here over on the other side. If you're just coming from a mountain here, you get a singularity. That's what we're trying to avoid. We think that in quantum gravity you don't get singularities. Quantum effects always smooth out a singularity. So if you want no singularity here, you got to have a classical solution on the other side. So he really needs that point-like universe on the other side. Li-Jing Li and I were saying the universe isn't made out of nothing. It's made out of something, a little tiny piece of itself. And you can do this with a closed time-like loop, with a little time machine at the beginning. So this is Vilenkin's model. Stephen Hawking has a model that looks exactly like this, and same thing going on. But Hawking commented that the south pole of this, that point at the beginning, is not really any different from the other points. So you've just got a sort of boundary there. And the universe is starting off with a boundary here. Space-time ends here, and there's this little Euclidean section that's on the bottom. These are both sculptures, four-dimensional sculptures that are just sitting there, okay? But they have causal things going on in them microscopically. If you look at it, you can see world lines of photons intersecting things, shaking charges, things like this. And so locally, this model has a boundary at the bottom. And our model has a periodic boundary condition at the bottom. Our model has the property that every event has events that are preceding it. Okay, Mr. Diaz, who compared these two models, said they were quite complementary. And he had analyzed the stability of our model. Our model is stable because if you sent a gravity wave around here, it would just keep losing energy as it went around. It would make a finite perturbation. It wouldn't disturb things. So this is stable. And he said it was quantum mechanically stable as well, if this loop were small enough. So he commented that these two were quite complementary. It brings forward the idea that maybe if you looked at the final quantum theory of gravity, these two models actually might look the same because time and space get confused when you get into the early days here. But ours has space-time here, and every event has events that preceded it that we would say were causing that things to occur there.
I hope that this gentleman here, the Southern gentleman, gave you a good picture of this sort of infinite recursion model that you see about the Big Bang. It's almost Ouroboros kind of snake.
It was
eating
hard
its
for me
tail.
to follow. You would have to summarize it for me. Can you summarize it?
Yeah,
in
yeah.
any way
So-
for me? I
so
couldn't
the-
really keep up.
So the way that these different models, so my impression of Penrose's model is that he kind of glosses over what the Big Bang looks like
Okay.
in this once the photons hit the infinite boundary.
Okay.
Sort of.
Well, they never hit the infinite boundary.
Well, right, but
okay.
the beginning is the end, is
Yes.
what his argument is.
Right.
However, the mathematics is kind of it's there's a lot to be desired.
Oh, there is.
Yeah,
Why?
because the lectures that he gives is more like a
Conceptual.
yeah,
Yeah. Okay.
and the papers that he's published are a little bit they're more mapping of the general logic of
right.
of the extension of what the birth and cycle, or the cycle of the universe, or the cycles of the universe.
So where does this guy come in?
So where these other
Foghorn.
competing models,
I'm sorry. I
so
had to.
so to kind of give another picture here, I wanted you guys to maybe get a sense of the competing models that include more modern conceptions of like what the space time looks like.
And this is all related to the conformal cosmology.
Yes, because these are all competing in the same field.
But I'm saying, is this conformal cosmology? Or
No,
these
no.
competing theories with conformal cosmology?
Yeah, it's competing theories with CCC.
Oh, okay.
Yeah. So
Well, I
CCC
wanna know
has
about
its own,
CCC.
but CCC is its own. I mean, you'll gather from the videos in itself.
Yeah.
It's very. How would you say? It's not gaining traction.
Yeah.
Because of the compliments that not the compliments, but the questions that arise
I see.
that have not been adequately answered. For instance, I have this. I have one more piece of literature here that I kind of want to
Okay.
bring up. It talks about why physicists have this. Why Penrose's idea of the cyclical universe is not really. It's not really gaining traction. For one, is the fact that Penrose's observations on how we should see fingerprints from ripple universes that are born, or sorry, that were born previously, looking at WMAP, physicists cannot recreate that looking at the same data set.
What do you mean? With current models or with CCC?
With CCC, like they can't. Like his particular
right,
model about
okay.
the creation of the universe.
Right, that makes sense.
Yeah.
Well, does it? I don't really know if it makes sense or not.
By the way, he won.
The WMAP would be different for everyone, I would imagine.
Why?
Because it's a cyclic process, right? And your photon, let's just imagine. Well, I'm conceiving of it in the way that I created myself because I don't really understand it. Like I don't understand the moment. I don't understand what happens at the end of the photon cycle to create the new Big Bang, right?
Right.
So what I imagined, or what my filler material was, that there's a decay of the photon, and the photon decays into a bunch of different particles. And if that's the case, then that means that would mean that the cosmic background for each event would be different. But that's my completely made up way, right? Because I don't understand what Penrose's conclusion was for the Big Bang to occur again. Like all these different Big Bangs at the end of the cycle. I don't know. I don't understand that part at all. I was hoping that video would tell me something about Mr. Red Dead Redemption over here. I couldn't really get what he was trying to say.
That's hilarious. So the testability, or the death knell for CCC, is that it should give it, like we were saying, it should give a fingerprint or something of the previous universes, but we see no evidence of that.
I thought they did with the gravitational waves.
Well, that's what he was selling. But
false.
False. So
as Dwight Schrute would say.
There is no leftover glow right now. There's no sense of there was a universe that existed before ours. Because his model is more linear, as some of you will see. Well, it's presumed to be more linear. That has a logical sequence to it. Penrose.
Okay. As opposed to
these other models that try to build a recursion. In sort of these models that talk about like the universe being born out of quantum fluctuations, meaning the uncertainty principle had an initial spark that you reach a singularity and then you tunnel to a classical system, kind of like what he was showing a picture of what you have, the initial conditions of the universe being in a quantum fluctuation, and tunneling necessarily presumes that you reach a lower energy state, because essentially the universe would have to have been some asymmetry, so that you go to a lower energy state, which would be, I guess, the classical universe, right? You're like, sure.
This is all shit that I don't know anything about, so you're out in the open for this one.
Okay, well, let's see if we can the final video. This is a very short one. It's a 3-minute video.
Yeah.
They talk about it in the previous video of Alexander Vilenkin. He had an interesting paper that hopefully he can.
Is this on CCC?
No, this is not on CCC. This is a competing theory to CCC.
Okay.
Yeah.
So it appears that the question of origin of the universe does not have a satisfactory answer.
It's Russian discussing.
Suppose I tell you what happened before inflation, and then you could ask us what happened before that. There is one scenario that breaks out of this infinite regress of questions, and this is the idea that the universe was spontaneously created out of nothing. So this is a pretty strange proposition for a physicist to make, because we know that there are laws of conservation of energy, for example, and how can you create something out of nothing? Even Lucretius was telling us that you cannot. However, it is a mathematical fact that a closed universe, that is, if you have a universe which is closes on itself, like a sphere, for example, closes. So in such a universe, the positive energy of matter is exactly compensated by the energy of gravity, which is always negative. So the total energy of a closed universe is necessarily zero. There is no conservation law that forbids creation of a closed universe out of nothing. And in quantum mechanics, anything that is not forbidden by conservation laws necessarily happens with some probability. So quantum mechanics allows a spontaneous nucleation, you could say, of a closed universe out of nothing, where by nothing I mean a state which has not only no matter, but also no space and no time. It is a great mystery of how this tunneling of the universe happens. And the mystery is that the same laws of physics that describe the evolution of the universe once it has appeared, the same laws describe this process of quantum creation of the universe. And this seems to suggest that these laws were there, the course there, even before the universe. That the laws are somehow more fundamental than the universe and have some Platonic existence.
Okay, well, this guy, it's in essence,
Yeah.
what have you gathered?
Something about the quantum fluctuations are what create the universe. And it's interesting because it's another one of these like cyclic processes, just like Penrose. Mm-hmm. It's really interesting how all these guys are coming to like these I don't know if there's influence.
There might be, yeah. There's overlap for sure.
It would be really interesting if they're all coming to these conclusions with this kind of cyclical processes independently. I doubt it, though.
I doubt it's independent.
Yeah, but it's pretty interesting how it has similarities to the conformal cyclic cosmology that Penrose is pushing out here.
Right, right. The Kentucky guy, he's got his.
The Colonel, you mean?
You know what? All respect to him. I would love to have him on the show for the
God.
record.
I don't know if I could. I don't know if I could stay awake.
Oh,
He
well,
starts talking about Pope Francis.
he would be a great
I'm
guest.
gonna be asleep on this show.
I'm going to invite him on
All
the
right,
show.
I'll stop being mean.
Well, we could. I would love to have him on. I would love to have this guy on. They have, and then to see their opinion on CCC to see what they have to say.
Can you maybe explain, Juan? Give us a synopsis of what's going on with the quantum fluctuations here.
Yeah, the quantum fluctuation picture is sort of what the argument is that if we look at the universe is sitting in there's a picture of a potential, the lowest potential state. Oh, the universe started at a how would you say?
Some kind of ground state energy.
Yeah, some kind of ground state energy. But the thing is, there was the argument that it was spontaneous. Is we have this concept in physics called spontaneous symmetry breaking, where there's a lower energy state accessible to the quantum system, so you can tunnel through a barrier to a lower energy configuration.
Oh.
And that's the argument that some physicists are saying, well, it's kind of interesting because when we see this in quantum mechanics where there is spontaneous symmetry breaking in systems where you do have a quantum you have a quantum how would you say, situation or environment or something, and then the particle tunnels to a classical or sort of starts behaving classically in these energy, how would you say?
These new energy wells, these lower energy states.
Right, right.
Yeah. I don't quite understand. It's very abstract, right?
Yeah.
Because when you say particle, I assume you also mean the particle as the entire universe.
Right. In this
Yeah.
primordial soup, it's
tunneling to other lower ground state universes?
well, in this particular model, it's more of like there's a nucleus. The initial universe is a nucleus. You don't
Okay.
presume that other universes started. It started as a soup,
Okay.
and there's sort of just quantum fluctuations, and then the probabilistic nature of having that necessitated that you tunnel spontaneously to the universe we see today, which is the ground state, I guess. Doesn't make sense?
No. Not to me. I don't get it.
I guess an assumption that physicists make is that we are at the ground state. This is the lowest energy configuration
For the universe.
for the universe.
Okay.
So
I don't even know what that means. What would a high energy state for our universe be?
what do you mean?
Like we're at the low state of the universe, right? The lowest energy state for the universe. What would a high energy state of the universe be? An unstable universe?
Well,
What does an
the
unstable
initial
universe
conditions
look like?
would be that there's extremely ordered, right?
Okay.
But then that quantum fluctuation picture, I don't know if it paints that. Maybe it does.
I don't know. I'm not prepared for
primordial
this. So either you have to carry it or you're gonna have to tap out because I can't. help you.
No. I'm saying I'm questioning. I'm trying to have a discussion about what the primordial, the primordial era looks like.
I don't know. It's the quark gluon plasma, right? Is that what you mean?
Yeah, I mean, there's the plasma era. Yeah.
Okay.
But that's
I'm
I
not
guess
sure.
That's different.
I don't know, bro. This is
All right, so we'll skip through that, but we'll go ahead and go into final thoughts.
okay.
Yeah.
All right.
So what's your take on CCC versus
quantum fluctuations?
Yeah, like because he doesn't seem to incorporate.
Is Colonel Sanders' theory quantum fluctuations as well?
Yeah, it's based on.
Okay.
It's based on quantum fluctuations. Yeah. So, today the leading competing theories is that we live in because of inflation, we think that we live in a bubble universe, or sort of like how would you say? a bubble universe. It's got its own laws, it's got its own stuff going on, but there are more than one universe that exists. I don't know if there seem to be a lot of smart guys that believe it. We know a lot of cosmologists, like Sean Carroll. He's
The
one of
bubble
these
universe.
guys, the bubble universe guys, the multiverse
And that's
guys.
like what? The universe is made from membrane collisions or something?
Yeah, it's like a space-time foam, and then
Yeah,
it just
yeah.
kind of bubbles up
Okay.
from the initial spark and all that.
Well, that's a whole nother podcast. I
Yeah,
don't
I
know
know.
anything about it.
Yeah, me too. But the it differentiates. CCC differentiates itself in being more linear and trying to give some insight into inflation not leading into multiverses. He doesn't think that there are sort of parallel universes.
Right. He's saying that it's all contained in one universe. It's just an illusion because infinity becomes finite. Well, not finite, but this interesting mapping, this conformal mapping between beginning and end of a universe cycle gives the illusion that there's kind of a reset or something.
Yeah.
But it's just continuously infinite down the line.
Which I appreciate his approach more because it seems to me more logical.
Yeah, I love Penrose's logic. I mean,
Yeah.
it's just, to me, it was like just I just
Poetry?
was giving it a chef's kiss. 'Cause It's
Poetry?
just such a cool idea.
Yeah.
Although I don't know how many legs it has to stand on. I mean, I thought of so many gripes with the theory just off the bat, and I just felt like it feels wrong
Yeah.
until I really analyze everything. But I mean, it's a beautiful thought. At the very least.
Yeah. I like the logical flow of it, but I don't think it maps to what we observe fully. These competing theories, as we're seeing right now, he doesn't really include a lot of, or he doesn't really talk about a lot of the quantum mechanics, what the quantum mechanics look like in the beginning of the universe, as far as we know.
Yeah, I'd like to see a little bit more proof and a little bit more addressing of some of the kind of obvious things that people might come up with as counterpoints to the theory. Then I can maybe be more convinced, even if it's conceptual. It doesn't have to be mathematical, but
Right.
like I mentioned with the big rip and the photon decay, and some of the things like Calabi-Yau manifolds with the 10 dimensions of string theory, and maybe even address like quantum mechanics in the sense that being at the quantum scales, because it's almost like if your universe keeps going down lower and lower and lower in these scales,
It's
technically,
fractal, yeah.
yeah, it's almost like then it's almost like weird, because it's like the large scale becomes the small scale. So it's almost like, how can that be compatible with our conceptions of like quantum mechanics and GR, because we know that the scale matters.
Right.
But is it just that because the scale information is all lost at the recreation of this new cycle, that it's almost just an illusion, and just the particles are now shrunken in proportion to this new universe, to where everything's exactly the same, and the universe really has this recursive property? Yeah, I would just like to know more. Like, I would like him to just attack more counterpoints to the theory, conceptually even.
Yeah, I agree. The other gripe that I had was about his whole analogy about clocks. Like, if we're talking about, he's saying that mass is
The scale information.
the scale, yeah, which I had never really conceptualized up until he brought up the point. But if we're talking about the proportionality between energy and mass and energy and frequency, and the constant there being the speed of light, it seems to me like if a photon
Has a frequency. Why can't that contain?
why can't that decay? Well, yeah, I mean, I what were you going to say?
I was gonna say, I was wondering if we had the same thought,
Yeah,
because I had this thought
I'm
too.
thinking,
Yeah, I was. Yeah, I'm glad you brought that up too, because that was another gripe I had that you just reminded me of. a photon has a frequency as well. So why can't the scale information be contained within the photon as well?
Right.
Because a photon has a clear oscillation of electromagnetic field. And you could technically map, that wavelength to some kind of scale information. In fact, we even measure the meter using how long it takes a photon to go X amount of light seconds or something.
Right.
So I don't understand why he says mass is the only way.
There's no metrics after, or there's no meter stick after the universe. I guess.
But you can time it with a watch. Let's say like a pretend clock. Or maybe he's saying that because of GR, relativity, because time information is relative. Maybe that's why. But then I'm thinking, why is matter so special?
Oh, I guess it's because his argument is that mass, because it affects gravity, photons don't interact with space-time.
They do.
Photons
are affected.
Oh, yeah, they
by
do
gravity,
interact.
Yeah.
But the thing is, mass.
But they don't make ripples in space-time, I guess. Is that it?
Right. They
why
don't
would that
interact
matter?
with space-time, meaning they might not interact with the gravitons or something in this little model here.
No, I don't like that.
No?
No.
The from what I gather, is that the photons don't interact with space-time, right?
They do, though.
What do you mean? In
They
what
don't
sense?
influence space-time,
Okay,
but
yes.
space-time influences photons.
Okay, thank you, yeah. That's a better way to put it.
But matter, of course, it's both ways, right? Space-time is influenced by matter. Matter influences space-time.
But you can't have clocks measured. Because there's no... Essentially, he's arguing that there's no time
Right.
anymore.
Once all matter's gone and it's just
If
photons.
there's only photons, there's no change.
Okay.
There's no time.
Oh, I see.
Yeah.
Because they're the only things that exist in that universe, so there is no way to measure anything. And I guess he's saying because matter, automatically when matter exists, there is time. Because now matter has this frame of reference where distance and time exist. Whereas photons have no conception of that because at the moment of creation, they're also at the moment of death at the same time in some sense.
Yeah.
Actually, can a photon even die?
That's what the decay question is.
No, it's
To
not.
me.
It's actually even
Oh,
a
it's
separate
not.
one. Because a
Oh, okay.
photon, like imagine with photon...
Well, it can't be destroyed.
Right. But imagine, like we were talking earlier about how when the universe expands, the photon's wavelength gets elongated, right? That just means that the photon frequency just gets lower and lower and lower and lower and lower, but it never reaches zero. So I don't even know if a photon can even, like... I mean, yeah, the photon decay is a different kind of death, but this is even another version I'm thinking of where it's like the photon frequency, it's just losing energy, but it never hits zero.
Mm-hmm.
Is that true? I don't know if it's true.
Well, the wavelength, wait, hold on. We were
Because
saying...
eventually it will go, and then that's even more of a problem too, because then it's outside of the visual spectrum. And then it's like if the photon is the one that creates the Big Bang event, if you're already outside of the visual spectrum of electromagnetic spectrum, then an identical universe would not be created.
Well, what does the energy look
think.
like for a photon that's so... The wavelength is so large, right?
Yeah. Like the max, I guess, would be a wavelength the size of the universe, the diameter of the universe.
Right.
Which, I mean, that's not against laws of
Fascinating.
physics, is it?
No.
I don't think so. It just gets longer and longer and longer and longer.
And then what the fuck happens?
I don't know.
Well,
this is why cosmologists
They're the
are
most
like trippy. Yeah, they're the most high. They're on some trippy shit, so I don't even know, man. It's like...
Yeah, you're talking about the wavelength of the universe getting so large, the scales of...
Yeah, it's just like, imagine the limiting case. It's the diameter of the universe. I don't see any reason that can't be.
Interesting. I wish I knew more.
Yeah. But yeah, this is why Penrose, I think he, like, for this particular theory, he needs to come up with numerous counterexamples and then debunk them one by one or explain a conceptual rebuttal for all of them. Because it's a really creative and interesting idea, but they're just not enough to convince someone to ever invest
Wait a minute.
time into.
If the wavelength gets larger, what does that say about the uncertainty principle? If we're talking about quantum effects. I mean, the wavelength is proportional to the momentum, right?
Yeah.
In some, inversely?
Yeah.
Yeah.
I think.
Right?
Is that true?
Well, because mv is the
you're
momentum. So
P
it's
equals h over lambda, or
Yeah.
hc over lambda, or
yeah,
no,
yeah.
something equals hc
MV,
over lambda. E equals HC over lambda.
MV, which is in the picture of frequency. It's frequency over lambda, right? Is velocity? Velocity is frequency.
Velocity is
No, it's
lambda f.
Lambda f.
Yeah.
Yeah. Thank you, Jesus.
Yeah, it's a little bit.
I had to think about the units here.
Yeah.
Lambda f.
Lambda
so
f.
actually, velocity is proportional to lambda.
Yeah.
So the
Momentum is proportional to
the wavelength.
frequency. Or wavelength.
So then that means that in that picture of the universe, where the universe is expanding, and the wavelength gets infinitely large, that means the position of the particle is really uncertain.
Yeah, because it could be anywhere in the entire universe, I guess.
Yeah.
Because it's stretched out over the entire universe. But then at the same time, it is the whole universe in some sense.
Which is boom. That is the whole universe.
Oh boy, we're getting there now again. Let there be light.
That photon is the universe.
Yeah.
Let there be light.
I don't know. We're probably sounding cosmologists right now. I'm sorry, guys, if this is like killing your brain.
But please, actually, this is a great moment to this is more of a call to action for cosmologists to come and talk on the show about this. I would love to get some of these guys on, and I'm sure we could, because if they're willing to do a documentary like this, whatever this channel is, we could definitely.
With the chick from Zero Dark 30.
Exactly. But I would frame it in the language of like, hey, this is like a talk. You're giving a talk. You know, I mean, most conferences don't really have an audience of 5,000 people. You know,
Right.
So.
Yeah, we actually have a substantial. But if we want to count our real audience, it's like 400 to
1,000.
Yeah, people.
Yeah.
Which is still pretty good.
That's pretty good.
Yeah.
So maybe we could get some of these guys on. I would love to have some of these guys on. I would love to ask more questions, because cosmology is one of these things that grabs a lot of people. And me and Terrence, as you see, we have a bunch of questions about the origins of the universe, and parsing through this is we don't have guide stones.
Yeah.
You know,
We would need to do a lot of legwork to really even begin to go through some of these things, because we don't have the cosmology intuition yet to know how to just fly through equations or fly through things
True.
to just find out what's going on.
we could talk about GR. We can understand where that comes from and all that.
Yeah.
But
It'll take a good bit of time, though.
yeah. Well, anyway, folks, make sure to like, share, comment, subscribe.
Yep. Check out Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok, and then Patreon.com if you want to support your boys. 30-minute audio podcast, Discord access, maybe some more stuff in the future.
Yep.
And did I say Patreon.com/Eigenbros?
Yeah.
Okay, good.
All right.
That's it.
And that's it. See you later.
All right.
Peace.